Have you ever stopped to really think about it? Could something be in two places at the same time? And how could two particles remain connected even when they're separated by light years? Tonight, we'll explore that stillness, the quiet strangeness beneath ordinary reality, the hidden layer where almost anything becomes possible. Welcome to Knowledge to Fall Asleep To. This channel is built for calm and curiosity, a place where you can learn something new about the universe without rushing through it. Before we begin, I'd love to know, where are you watching from and what time is it there right now? It's always fascinating to see how far these silent journeys can reach. If you enjoy peaceful science and gentle discovery, please like the video and consider subscribing. It truly helps. And to everyone who's already subscribed, thank you. You're the reason this small, quiet corner keeps growing. Don't forget to turn on notifications so you won't miss what comes next. Now, let's drift slowly through science and space. I hope this video won't be too interesting, the kind of interesting that keeps you awake. But if it is, at least you'll fall asleep knowing a little more about the most mysterious part of physics. Because once you look closely enough, the universe begins to behave in ways no one can fully explain. Quantum physics began with a problem that simply wouldn't go away. Light sometimes acts like a smooth, gentle wave, spreading, bending, interfering with itself. And then, just as strangely, it behaves like tiny particles, small, counted packets of energy. Matter so solid, so predictable at human scale, turns out to shimmer with probability. The deeper scientists looked, the more the old rules started to break apart. Out of that confusion, a new idea emerged. Everything is built on uncertainty. Energy doesn't flow continuously. It arrives in steps, discrete jumps called quanta. Particles don't travel along one single path. They explore every possible path until something forces them to choose. Even emptiness isn't truly empty. The vacuum trembles with invisible energy, flickering in and out of existence like a quiet pulse beneath silence. Tonight, we'll move through these calm revelations, one by one. 101 moments where logic bends, and nature shows its strange precision in mathematics. You'll hear about superposition, where something can be two things at once. About entanglement, where particles stay linked across light years. And about the eerie hum of the vacuum, space itself whispering even when everything seems perfectly still. Each fact is like a door opening into a smaller world, a world where order becomes fragile and uncertainty becomes a different kind of order. So let's begin with the smallest steps of all, those tiny foundations that quietly built the modern universe from the inside out. And among the most astonishing of these ideas is superposition, the principle that at the quantum level, things don't exist in just one state or another. They can exist in many states at once. And this is where quantum physics stops feeling like a set of rules and starts feeling like a different kind of reality. At the quantum scale, things don't exist in just one state or another. They can exist in many states at the same time. A single atom can spin clockwise and counterclockwise at once. A particle can carry every possible route from one point to another simultaneously. Even the simplest question, where is it, becomes slippery, because the answer isn't one location. It's a whole landscape of locations, overlapping possibilities, until something, usually a measurement, forces the universe to choose, to picture it Imagine flipping a coin. In the everyday world, it's either heads or tails. Even while it's spinning through the air, it's still technically one or the other. We just don't know yet. But in the quantum world, before the coin lands, it isn't hiding an answer. It truly holds both, heads and tails layered together in a delicate blend of probabilities. Only when it's observed, only when the system interacts with its surroundings, does it settle into a single outcome. That fragile in-between is superposition, a temporary balance between everything that could happen and everything that might have happened. Schrödinger made the strangeness unforgettable with his famous cat, alive and not alive, living and dead. It was never meant to be taken literally. No one expects a real cat to hover between life and death. The point was simpler and sharper. When you scale quantum rules up to human size, they sound absurd. The cat's fate is tied to a quantum event inside the box, something as small as the decay of a single atom. Before anyone looks, the atom has both decayed and not decayed. And in that strange accounting, the cat is both outcomes at once, until the box is opened, or until the wave function collapses into one story. It isn't horror, it's a reminder of how quantum possibilities fade into classical reality when observation and interaction finally happens. And as abstract as this sounds, it's not just philosophy. It's the backbone of modern technology. Every quantum computer, for example, is built on superposition. A classical bit must be either 0 or 1. But a qubit can be 0 and 1 at the same time, held in a controlled overlap. That allows quantum machines to explore vast numbers of possibilities in parallel, like trying every combination of a lock all at once instead of one by one. But superposition isn't merely being in two states. The deeper point is how those states combine. Each possibility carries something like a phase, a hidden rhythm that decides how it will reinforce or cancel the others. When waves overlap, their phases can add together to create bright peaks or erase each other into darkness. Quantum systems behave the same way. Probabilities interfere. Some outcomes are amplified, others are quietly erased. This is what creates the interference patterns in experiments like the double slit, where particles seem to know about paths they didn't take. Those bright and dark bands aren't random. They're a precise record of how possibilities interacted before reality chose a single result. Once you accept that the universe is built from probability waves, superposition stops sounding mystical and starts sounding inevitable. A particle's wave function contains all its possible states, each with its own amplitude and phase. When we measure, yes, we don't simply uncover a hidden truth, we select one outcome from that probability landscape. Scientists have even seen signatures of superposition in surprisingly large systems, sending complex molecules through double slit-like setups and still watching interference emerge. The larger the object, the harder it is to preserve its quantum behavior because the environment constantly touches it, scrambling the delicate coherence. That slow destruction of overlap is called decoherence. But the principle remains. From photons to electrons to atoms, the quantum nature is always there, waiting just beneath the surface. It's tempting to imagine superposition as hesitation, as if particles are simply undecided. But that isn't quite right. The system isn't confused. It's complete. It holds the full choir of possibilities, each balanced against the others until something disturbs the harmony. In that sense, superposition isn't a flaw in reality. It's how reality keeps its options open, and it also shows something subtle about observation. It isn't passive. To measure is not merely to read, it's to interact. And interaction forces a quantum system to merge with its surroundings, to lose coherence, to collapse into one consistent story. Whether the observer is a scientist, a camera, or a stray particle of dust doesn't matter. What matters is the exchange of information between the system and the world around it. Even after a century of experiments, physicists still debate what collapse truly means. Some interpretations suggest every outcome happens, each in its own branch of reality. Others argue the wave function never collapses at all. It only becomes entangled with everything else, so observers perceive a single, stable slice. But no matter the interpretation, the practical fact remains the same. Superposition is real. Its effects are measurable, predictable, usable. Without it, the world would lose its shimmer. Lasers wouldn't amplify light so cleanly. Atoms wouldn't form stable bonds. Matter would fade into a dull, featureless monotony. Even photosynthesis appears to exploit quantum overlap, letting energy explore multiple routes through molecular networks to find the most efficient path. Look at it this way. Superposition isn't an exception to the universe. It's the universe's hidden grammar. What makes reality flexible, adaptive, and quietly efficient. But the quantum world holds an even deeper twist, one that's been misunderstood more than almost anything else: uncertainty. In everyday life, uncertainty feels like ignorance, like you simply haven't searched hard enough. But in quantum mechanics, uncertainty isn't a limitation of your eyes or your tools. It's woven into the structure of reality itself. Nature isn't merely hiding the answer from you. In some cases, the answer doesn't fully exist until you ask. It's the universe's handwriting, its quiet grammar for describing the very small. At first, it's tempting to think that built-in randomness would make reality messy, unstable, chaotic. But the opposite is true. In the quantum world, uncertainty doesn't destroy order. It creates a different kind of order. Statistical precision so sharp, it's almost unsettling. The spread of possibilities follows strict mathematics, and those equations make predictions with crystal clarity. Lasers, atomic clocks, transistors, quantum sensors, so much of modern technology depends on the reliability of quantum uncertainty. If the world were perfectly determined, many of these devices wouldn't work at all. It's the microscopic blur that makes them possible. You can even see uncertainty at work inside atoms. Electrons don't orbit a nucleus the way planets orbit the sun. They exist in quantized orbitals, stable regions of probability shaped by the uncertainty principle. The tighter an electron is confined, the less certain its momentum becomes. And that balance between what can be pinned down and what must remain spread out literally defines the structure of the atom. It's also why electrons don't simply collapse inward. They can't simultaneously have a perfectly precise position and a perfectly precise momentum. The exact combination that would let them spiral into the nucleus. Quantum uncertainty creates a minimum safe radius, a built-in buffer that keeps atoms from breaking. The same principle echoes at a grander scale. In white dwarfs and neutron stars, matter is crushed into impossibly small volumes. As electrons are squeezed tighter, their momentum uncertainty grows. And that swelling uncertainty becomes a real outward push. degeneracy pressure, strong enough to hold an entire star up against gravity. In a very real sense, Heisenberg helps keep the universe from collapsing into silence. Uncertainty even reaches into the act of seeing. To observe anything, yes, you must interact with it, bounce photons off it, probe it with fields, disturb it just enough to extract information. But every photon gives an electron a tiny kick of momentum. The sharper the picture you want, the shorter the wavelength you need, and the more disruptive each photon becomes. This isn't a flaw in our instruments, it's a built-in trade-off of the quantum world. And that trade-off reshapes the idea of knowledge itself. Perfect prediction is impossible, not because nature is chaotic, but because probability, not precision, is the language of truth. Physicists don't try to forecast one single outcome. They map the landscape of possibilities, and within that landscape lives an extraordinary, dependable order. Uncertainty doesn't hide reality. It defines it. Every gain in certainty comes at a cost somewhere else. Which brings us to measurement. In classical physics, measuring is like checking the temperature of tea. You reveal what already exists. In quantum mechanics, measurement doesn't just reveal reality, it helps select it. Before measurement, a system can rest in superposition. After measurement, one outcome remains, chosen according to the wave function's amplitudes, which can interfere to shape the probabilities we see. A single result can look random, but across many trials, the statistics are exquisitely predictable. Like dice, you can't predict each roll, but you can predict the distribution. This probability-first universe sparked a famous tension. Einstein resisted the idea that randomness was fundamental. God does not play dice. Yet experiment after experiment suggests the randomness is real, intrinsic, or irreducible, only governed by rules so consistent they would make a casino jealous. Measurement also blurs the boundary between observer and observed. To measure is to interact, and interaction entangles the system with the device and with the environment. That's where decoherence enters. Superpositions don't vanish because quantum laws stop working, but because coherence is drowned in countless microscopic interactions. Decoherence is the bridge from quantum possibility to everyday certainty, turning measurement from a mysterious switch into a gradual transition, from many potential stories to the one story that remains accessible. Even then, the quantum world keeps its options open longer than we expect. A delayed choice in quantum eraser experiments show that what matters is not what really happened, but what information remains available. And from that information-shaped reality, we step into something that sounds like science fiction: entanglement. The same underlying logic also divides the particles themselves. Fermions give matter its stubborn stability, its refusal to be squeezed into nothing, because identical fermions can't share the same quantum state. That exclusion is what creates degeneracy pressure in white dwarfs, and what ultimately leads to neutron stars when electrons and protons merge into neutrons. Bosons, in contrast, are the sharers and messengers. Photons carry electromagnetism, gluons bind quarks, and the Higgs field gives particles mass by interacting everywhere in space. The difference comes down to spin, half integer for fermions, integer for bosons, changing the symmetry of their wave functions and the statistics they obey. Bosons can even crowd into one shared state, producing spectacular effects like the Bose-Einstein condensate, where many atoms behave like one coherent superatom. In this way, fermions build structure through refusal, while bosons build coherence through sharing. Together, they shape everything, from rock-solid matter to starlight. And there's one more step deeper. In modern physics, particles and forces aren't the final layer. Fields are, not fields you walk through, but invisible presences that fill all of space, rippling and interacting everywhere at once. What we call particles are localized excitations, quantized ripples of those fields. A light is a vibration of the electromagnetic field. Electrons are excitations of the electron field, and forces are energy exchange between fields. Two electrons repel not because invisible hands push them apart, but because they disturb the electromagnetic field, and that field responds by exchanging momentum through photons. Quarks feel the strong force through gluon exchange. The same principle repeats everywhere. Forces are simply different ways fields talk. And one of quantum field theory's strangest consequences is that the vacuum, so-called empty space, isn't empty. Remove all matter and radiation, and the fields still remain. They can't be perfectly still. Quantum mechanics forbids it. Instead, they jitter with zero-point energy, fluctuating at every point in space. For brief instants, our particle-antiparticle pairs can appear and vanish, virtual particles borrowing energy and returning it almost immediately. We can't see them directly, but we can measure their fingerprints, tiny shifts in atomic energy levels that prove the vacuum is active, not inert. This something from nothing has real effects. In the Casimir effect, two uncharged metal plates placed extremely close together attract because the gap restricts which vacuum fluctuations can exist between them. And on cosmic scales, the small but measurable energy density of empty space is tied to the universe's accelerated expansion. Though why theory and observation disagree so wildly remains the cosmological constant problem. The elegance of the field picture is that it unifies everything into one language. Waves and particles, matter and energy has become different expressions of the same idea. Particles are quantized ripples and forces are exchanges. Empty space stops looking like a void and starts looking like a deep, quiet ocean. In this view, higher frequency vibrations appear as heavier particles, while gentler oscillations show up as light and radiation. The universe becomes a single orchestra of fields, building complexity from simple harmonies across space and time. Even identity changes. When two electrons scatter, there's no meaningful which is which. They're indistinguishable crests on one electron field, one endless ocean. That's why every electron is identical everywhere. Nature doesn't manufacture them one by one. It lets the same pattern rise again and again. Creation and destruction feel natural too. If energy is concentrated enough, it can excite fields into new particles. When excitations cancel, energy returns to the fields. Accelerators do this deliberately, smashing particles to reveal deeper symmetries. These fields are quantum at the core. Their vibrations come in discrete steps, and the Standard Model has predicted subatomic behavior with astonishing success. And yet, it isn't complete. It doesn't include gravity, and it leaves dark matter, dark energy, and the early universe only partly explained. Still, the big picture is quietly satisfying. The universe isn't a collection of separate objects moving through emptiness. It's a living tapestry of vibrations. where even the darkest space is threaded with fields, humming softly with possibility. It was revealed by experiments, turning points that cracked the comfort of classical thinking and replaced it with something stranger and far more accurate. From beams of light knocking electrons free to single particles painting interference patterns one dot at a time, these experiments didn't merely uncover facts. They showed us that reality is more subtle than anyone expected. At the start of the 20th century, physicists believed they understood light. It was a wave, smooth, continuous, predictable. Then the photoelectric effect arrived like a fracture line through that certainty. Shine light on a metal surface and electrons can be ejected, as if the light is striking them loose. Classical physics predicted that brighter light should always liberate more electrons, regardless of color. But nature refused. Only light above a certain frequency could eject electrons at all. Increasing the brightness below that threshold did nothing. A brilliant red beam simply couldn't do what even faint blue light could. In 1905, Einstein made a bold proposal. Light's energy isn't spread smoothly through a wave. It comes in discrete packets, quanta. Each packet, later called a photon, carries energy proportional to its frequency. Blue photons carry more energy than red ones. The photoelectric effect made it undeniable. Light can behave like particles, not just waves. Einstein would later receive the Nobel Prize for this work, and wave-particle duality became one of quantum theory's first great pillars. But the universe kept pushing. If waves could act like particles, could particles act like waves? In 1927, Davison and Germer studied electron scattering off a nickel crystal and found something that shouldn't exist in a classical world. Bright and dark bands, an interference pattern, the signature of waves. Their discovery confirmed Louis de Broglie's daring idea that matter has wavelength. Electrons aren't tiny solid marbles. They are wave-like entities that can diffract and interfere just like light. That set the stage for one of the most haunting demonstrations in all of physics, the double-slit experiment with single particles. Two slits produce an interference pattern for light, bright fringes and dark gaps. But when scientists send photons one at a time, or electrons one at a time, the same pattern still emerges slowly, dot by dot. Each particle lands as a single point, yet over time, the points build a wave-like fringe pattern, as if each particle interfered with itself, like it traveled through both slits at once. And then comes the twist. If detectors are placed to learn which slit the particle went through, the interference vanishes. Two clear stripes appear instead. Particle-like behavior, clean and ordinary. The conclusion is hard to avoid. Observation changes what happens. Reality doesn't finalize a single story until information forces it to. This experiment has been repeated in countless variations, using atoms, molecules, even large organic compounds, and the results remain astonishingly consistent. The universe seems to settle into one definite version of events only when the which path information becomes available. Until then, it remains in superposition, a mist of possibilities waiting to become real. The double slit isn't just about wave-particle duality, it's about the strange relationship between knowledge and existence. And when physicists went deeper still, they found something even more unsettling. Entanglement, a connection between particles that persists across distance linking outcomes in ways that challenge classical intuition. Einstein dismissed it as spooky action at a distance, arguing hidden variables must explain the correlations. But in the 1960s, John Bell turned philosophy into testable mathematics. He derived inequalities that any local hidden variable theory must obey. Over the decades that followed, beginning with Alain Aspect's pioneering experiments and continuing through increasingly precise loophole-closing tests, the verdict became clear. Quantum mechanics predicts correlations stronger than local hidden variable models can allow. And that is exactly what experiments observe. Entangled particles behave as if they share one unified state, even when separated by great distances. At the deepest level, reality seems built not from isolated parts, but from relationships that stretch across space. And those same correlations now power real technologies: quantum cryptography, quantum communication, quantum computing. As experimental tools became more refined, physicists began to demonstrate quantum effects in systems large enough to feel almost human scale. One of the most elegant examples is the SQUID, the superconducting quantum interference device. A squid is essentially a loop of superconducting material interrupted by one or more ultra-thin barriers called Josephson junctions. When cooled near absolute zero, electrons inside the superconductor form Cooper pairs that behave like a single quantum entity moving without resistance. In that loop, current can exist in a superposition, flowing clockwise and counterclockwise at the same time. By measuring interference between those two quantum states, squids can detect magnetic fields so tiny they can sense the subtle signals of the human brain or the faintest whispers of cosmic phenomena. All these experiments, photoelectric effect, electron diffraction, double slit, Bell tests, squids, tell the same story from different angles. Quantum mechanics is not a metaphor. It is the machinery of reality. And perhaps the most striking thing is how reliably it holds. No matter how strange the setup becomes, the equations keep being right. The quantum world may be counterintuitive, but it is astonishingly consistent, revealing the same truth again and again. At the smallest scales, reality is woven from probabilities, patterns, and relationships, which brings us back to decoherence, because it explains something that used to feel like a paradox. It explains why we don't see Schrödinger's cat both alive and dead, why planets don't occupy superposed orbits, why the world feels stable at human scale. But even here, decoherence doesn't destroy quantum mechanics. It hides it. Every macroscopic event, every flicker of flame, every ripple of air is still governed by quantum laws. Coherence simply doesn't last long enough for interference to remain visible. And once physicists understood decoherence, they gained a firmer way to talk about measurement. Instead of invoking a mysterious collapse, decoherence shows how quantum probabilities become classical through interaction, how the boundary between quantum and everyday experience is less a hard line and more a smooth transition. The world doesn't stop being quantum. It becomes too entangled with itself for its quantum strangeness to stand out. And now researchers try to do something daring, not merely observe decoherence, but control it, sometimes even partially reverse its effects by carefully engineering the environment. Superconducting circuits, trapped ions, and ultra-cold neutral atoms can be isolated enough for coherence to survive far longer than it normally would. These are the systems behind quantum computers, atomic clocks, and sensors sensitive enough to measure minuscule shifts, tiny gravitational gradients, subtle changes in Earth's crust at almost atomic resolution. In a poetic sense, coherence is the universe at its most harmonious. Probability waves singing in phase, a system vibrating as one. Decoherence is the return to noise, individuality, disorder, the familiar roughness of ordinary life. And both are necessary. Without coherence, the most distinctively quantum effects would never appear. Without decoherence, the world would remain a fog of probability, never stabilizing into the patterns we call reality. So the next time you see a laser draw a steady red dot on a wall, remember, you're watching coherence made visible. And in every flicker of candlelight, every sound, every sensation, decoherence is happening too. The graceful release of quantum order into classical calm. Between those two, wave and noise, harmony and loss, lies the rhythm of the universe itself. And when matter is cooled far beyond anything nature typically provides on Earth, when thermal noise is stripped away and the world becomes quiet enough, quantum behavior doesn't just survive, it takes over. In those extremes, atoms begin to lose their individuality and act as unified entities, forming strange and beautiful states of matter that follow the deepest rules of quantum mechanics. Two of the most striking are the Bose-Einstein condensate and the Fermi sea, opposites in behavior, yet both written in the smallest print of nature. Or to imagine a Bose-Einstein condensate, picture a cloud of bosonic atoms cooled closer and closer to absolute zero. At ordinary temperatures, atoms jostle and behave as individuals. But as the temperature drops, their energy spread narrows. Their wave functions begin to overlap. And at a critical temperature, often just billionths of a degree above absolute zero, the separate waves merge into one giant quantum wave. The atoms lose their separate identities and behave as a single coherent object. That is a Bose-Einstein condensate, predicted by Einstein and Bose in the 1920s, first created in a lab in 1995. In this state, countless atoms occupy the same lowest energy configuration, forming something like one superatom, where every part is aware of what every other part is doing. Nudge one corner, and the whole condensate ripples in response like a single synchronized thought. In some experiments, you can even see interference patterns within it, quantum wave behavior made visible on a scale approaching the human. A famous cousin of this idea is superfluid helium-4. Cool helium-4 below about 2.1 Kelvin, and it suddenly changes character. It becomes a superfluid, flowing with no viscosity, climbing walls, spilling over container edges as if gravity's rules have been rewritten, rotated, and it doesn't spin like an ordinary liquid. It forms an array of tiny vortices, each carrying a quantized unit of angular momentum, direct evidence that quantum rules still govern at macroscopic scale. Fermions, of course, play a different game. Because of the exclusion principle, fermions can't all fall into the same lowest state, even at absolute zero. They stack into layers, each new fermion forced into a slightly higher energy state, filling up a vast reservoir of states up to a boundary called the Fermi level. This is the Fermi sea, and it shapes the behavior of metals, white dwarfs, and neutron stars. In metals, it influences conduction. In white dwarfs, it creates the degeneracy pressure that resists gravitational collapse. And yet, fermions have a loophole. Pair two fermions together, and their spins combine into an integer, making the pair behave like a boson. That's the secret behind Cooper pairs and superconductivity. Superconductivity is one of the most magical promises of quantum physics made visible at human scale, current flowing forever with no energy loss. Below a critical temperature, as some materials suddenly lose all electrical resistance, not almost zero, but exactly zero. The story began in 1911 when Heike Kamerlingh Onnes cooled mercury to about 4.2 Kelvin and watched its resistance vanish. For decades, no one understood why. Then, in 1957, the BCS theory showed the mechanism. Electrons can form weakly bound pairs through interactions with a crystal lattice. Those Cooper pairs behave like bosons. They condense into a single shared quantum state described by one coherent wave function spanning the entire material. In that collective state, scattering that causes resistance is suppressed because the electrons are no longer acting as independent particles. They are moving as one synchronized wave. Superconductors also reveal the Meissner effect. When a material becomes superconducting, it expels magnetic fields from its interior. Place a magnet near it, and the magnet can levitate, held up by the magnetic field being pushed out. It's not just ordinary magnetic repulsion. It's a clear sign that superconductivity is a distinct quantum state of matter. Then comes an even stranger bridge between coherence and tunneling, the Josephson effect. In 1962, Brian Josephson predicted that if two superconductors are separated by an ultra-thin insulating barrier, only a few atoms thick, Cooper pairs can tunnel through with no voltage applied. Quantum tunneling on a macroscopic scale. And if a small voltage is applied, the resulting current oscillates at a frequency set with incredible precision by that voltage, linking electricity and time through one of the most exact relationships in physics. Josephson junctions became the heart of squids, which measure magnetic fields by detecting tiny phase shifts in superconducting currents. They're sensitive enough to detect minute variations, down to fractions of a trillionth of Earth's magnetic field, useful in brain imaging, material science, and ultra-precise sensing. Josephson effects are also so exact that they serve as a natural voltage standard, tying measurement directly to fundamental constants, the electron's charge and Planck's constant. And in the last couple of decades, these same superconducting circuits, built from Josephson junctions, have become one of the most promising architectures for quantum computing. Tiny loops of superconducting current can form qubits, holding superpositions and entanglement in circuits large enough to engineer directly. The challenge, again, is coherence. These circuits must be shielded and cooled to millikelvin temperatures inside elaborate dilution refrigerators, silver chandeliers of extreme cold, so quantum phases survive long enough to compute. Beyond computing, superconductivity has transformed technology. MRI scanners rely on powerful superconducting magnets. Particle accelerators use them to steer beams near light speed. Maglev trains levitate and glide on superconducting forces. An effect discovered as a laboratory curiosity in 1911 has become a cornerstone of modern science and engineering. All of it is the same story repeating in new forms. When noise falls away, quantum order doesn't vanish. It becomes visible. Yet even after a century of breakthroughs, superconductivity still holds mysteries in its silence. Researchers are still searching for materials that become superconducting at higher temperatures, ideally at room temperature. In recent years, hydrogen-rich compounds in certain rare metal systems have shown tantalizing results, becoming superconductors under crushing pressures. If that kind of behavior could be achieved under everyday conditions, the impact would be revolutionary. Lossless power grids, perfectly efficient motors, electronics that don't waste energy as heat. At its heart, superconductivity is a story of cooperation. It's what happens when countless electrons, normally repelling one another, fall into step and move as one. It's nature demonstrating that when individual particles surrender their independence and share a single phase, resistance can vanish. The Josephson effect and everything it enables, squids, qubits, or superconducting magnets, are reflections of that same harmony, many becoming one, noise becoming order. Most of us think of electricity as something that always rubs against the world, shedding energy as it moves. Superconductivity reminds us there is another way, quiet, perfectly organized, perfectly efficient. A quantum mechanism that is not chaos, but calm. The same rules that make the microscopic world seem unpredictable can, under the right conditions, create something almost impossibly exact. And while quantum mechanics can feel like it belongs only in laboratories or thought experiments, it quietly powers the modern world. Every screen, every smartphone, every computer chip is built on an invisible architecture of quantum physics. It lives in the light of LEDs, the timing of GPS signals, the hum of MRI scanners, and the current flowing through transistors. Those strange laws that govern atoms and waves aren't just curiosities. They're the reason technology works at all. Start with the transistor, the tiny switch that changed human history. A single computer chip can contain billions of them, each flipping current on and off faster than any mechanical part could ever move. The transistor works only because of quantum mechanics. Inside a semiconductor, electrons don't roam freely like they do in metals, and they aren't locked in place like they are in insulators. Instead, they occupy allowed energy bands defined by quantum rules. Between these bands lies a forbidden region, the energy gap, where electrons cannot exist. By adding tiny amounts of impurities, doping, engineers can sculpt how easily electrons can cross that gap, creating materials that behave like one-way streets for current or gates that open and close on command. Logic circuits inside your phone are, in a sense, carefully engineered landscapes of quantum possibility. The same rules that make quantum theory feel strange, discrete levels, tunneling, probabilities, are the same rules that make digital civilization possible. Without them, no laptops, no satellites, no modern world. From transistors, it's a short step to light. Quantum physics explains how light and matter trade energy, one photon at a time. That's the principle behind LEDs, light-emitting diodes, so common now that we hardly pause to notice how extraordinary they are. In an LED, electrons are pushed into a semiconductor and then fall from a higher energy band to a lower one, releasing the energy difference as a photon. The color depends on the band gap. Smaller gaps produce red, larger gaps produce blue. It's elegantly efficient because each photon is born from a single quantum jump, not from heat and waste. The same idea, sharpened to perfection, gives us the laser. A laser, light amplification by stimulated emission of radiation, works by pumping electrons into excited states and then encouraging them to fall back in unison, emitting identical photons. Those photons stimulate others to do the same, building a chain reaction. The light becomes coherent, wave peaks aligned with wave peaks marching in step. That's why a laser can cut steel, carry data through fiber optics, scan barcodes, and perform delicate eye surgery. Every clean red beam you see at a checkout counter or concert is a perfectly tuned quantum choir holding one note. Solar cells are built from the same physics, only reversed. Instead of turning electricity into light, they turn light into electricity. When a photon hits a solar panel, its energy can lift an electron across the band gap, freeing it to flow as current. That's the photoelectric effect again. Einstein's 1905 insight, now multiplied into one of the world's most promising energy technologies. Each cell is a tiny photon trap, converting sunlight into moving electrons that power homes, satellites, spacecraft. Quantum physics also governs something even more intimate than power: time. A normal clock keeps time through mechanical motion, gears, springs, pendulums. But an atomic clock keeps time by listening to atoms themselves. Certain atomic transitions occur with astonishing regularity. In the case of cesium, it's exactly 9,192,631,770 cycles per second. And that number defines the second. Modern atomic clocks are so stable they would drift by less than a second over time scales comparable to the age of the universe. GPS depends on them. Timing errors of mere nanoseconds can translate into position errors of meters. Your phone's navigation, airplanes, ships, financial systems, so much of the modern world relies on quantum precision, keeping the beat. Then there's medicine. MRI, magnetic resonance imaging, works by probing the quantum property of spin inside atomic nuclei, especially the hydrogen nuclei in the water throughout your body. In a strong magnetic field, those spins align like tiny compass needles. A radio pulse nudges them, and when they relax back, they emit faint signals. By detecting those signals and mapping their differences across tissues, an MRI machine builds detailed images of the body's interior without a single incision. It's a way of listening to the quiet resonance of atoms inside living flesh. Transistors, LEDs, lasers, solar cells, atomic clocks, MRI. All of them point to the same truth. Quantum mechanics is not confined to the lab. It is woven into everyday life. The light in your room, the internet carrying these words, the system that guides you home. Each depends on electrons leaping across quantized gaps and photons obeying probability rules first glimpsed more than a century ago. Even ordinary material properties, the sheen of metal, the transparency of glass, the hardness of diamond, come from quantum band structures and electron arrangements. Resistance in copper wires, the behavior of magnets, the very possibility of superconductors, all arise from the collective behavior of countless particles obeying the same microscopic laws. Every device around you is a quantum system scaled up and tamed. And as quantum technology advances, the boundary between quantum and everyday keeps fading. Quantum computers are beginning to perform specialized tasks. Quantum sensors are being built to detect subtle signals, gravitational ripples, underground structures, tiny shifts in fields. Quantum networks may one day enable communication that can't be secretly copied. But in truth, the quantum revolution already happened. It began the moment we learned to shape silicon's energy bands and capture the energy of a single photon. The world around you hums with quiet quantum precision. Every pixel that glows, every electronic pulse, every time signal belongs to an invisible orchestra. Electrons and photons and atoms performing their delicate symphony beneath the surface of daily life. And perhaps that's the most astonishing part. The strangest physics in the universe isn't hidden in distant galaxies or particle accelerators. It's right here, vibrating softly in your pocket, lighting your room, guiding you home, reminding you with every second that you live inside miracles so small they can be counted. And once you've seen that, it's natural to wonder if we can build civilization on quantum rules. What happens when we build computation itself on them? Classical computing is built on bits, 0 or 1, off or on. A qubit doesn't have to choose. It can hold 0 and 1 at once, suspended in superposition until measured. You can picture it on the Bloch sphere, North Pole as 0, South Pole as 1, and every point in between as a phase-weighted blend that can interfere with itself. That flexibility opens an exponential landscape. 2 classical bits can represent 4 possibilities, but only one at a time. 2 qubits can represent all 4 simultaneously. With 10 qubits, you reach over 1,000 combinations. 20 passes 1,000,000. 50 becomes an astronomically large space of possibilities. That's why quantum computing is so compelling. But superposition isn't the whole story. The real power appears when qubits become entangled, linked so the state of one can't be described without the others. Entanglement spreads information across the system in a way classical bits can't mimic. Quantum gates weave these correlations and shape probability itself, arranging interference so wrong answers cancel while the right ones reinforce. A classical algorithm searches step by step. A quantum algorithm can let many paths coexist, then sculpt the wave of possibilities so the correct path stands out. That's why certain algorithms matter. Shor's algorithm can factor large numbers dramatically faster than known classical methods, threatening today's encryption, while Grover's algorithm speeds up search through unstructured data. Other approaches promise breakthroughs in chemistry, optimization, and materials, especially for simulating quantum systems, which are naturally hard for classical machines. The catch is fragility. Superposition and entanglement don't last long before decoherence washes out delicate phases. And because you can't clone an unknown quantum state, you can't protect data by simply copying it. That's why quantum error correction is essential. One logical qubit encoded across many physical qubits, so errors can be detected and corrected without destroying the computation. Like hiding a melody in an orchestra so the theme survives even if one instrument slips. So the race isn't only about more qubits, but better ones. Longer coherence, higher fidelity, stronger resistance to noise. That's why platforms compete. Superconducting qubits, Josephson junctions, trapped ions, laser-controlled atoms, photonic qubits, light, and topological designs aimed at built-in robustness. There's something quietly poetic in it. A qubit hovering between 0 and 1 suggests uncertainty isn't a flaw. It can be a resource. Where classical computing relies on certainty, quantum computing thrives on possibility, but conducting a symphony of probabilities toward a definite answer. Quantum machines are still experimental, delicate, expensive, limited, but their potential is immense, and they hint at a deeper idea. We're learning in our own small way, to compute the way the universe already does, parallel, probabilistic, entangled. And yet even this freedom has limits. The quantum world isn't lawless. Principles like no cloning, complementarity, and the unavoidable disturbance of measurement are nature's guardrails, reminders that knowledge has a cost and context matters. In classical physics, reality feels like a library of fixed facts. In quantum physics, it feels more like a conversation, where the answer is written, in part, when you ask. From that same logic comes quantum communication. Security enforced by physics rather than puzzles. In quantum key distribution, QKD, a key is encoded in photon states. Any attempt to intercept or copy inevitably disturbs them, revealing eavesdropping through an increased error rate. In recent decades, QKD has moved from theory to demonstrations over fiber networks and free space links, including landmark satellite experiments, early steps toward a quantum internet. Then there's quantum teleportation, not moving matter, but transferring a quantum state using an entangled pair plus classical communication. The original state is destroyed, so nothing is cloned, while the receiver reconstructs the same state on their particle. It's real, repeatable, and foundational for future networks. Quantum tech also gives us true randomness. Classical generators are often pseudo-random. Quantum measurements can be fundamentally unpredictable. Quantum random number generators already exist, producing bit streams that are, in principle, impossible to forecast, turning the same uncertainty that troubled Einstein into a protector of digital trust. Distance remains the challenge. Quantum states are fragile, and entanglement degrades with loss and noise. Classical signals can be amplified. Quantum signals can't be copied safely. That's why researchers build quantum repeaters, extending entanglement step by step and linking segments through entanglement swapping. Slow, demanding, but consistent with nature's rules. And beneath all of it lies a shift in perspective. In quantum theory, information isn't detached. It's physical, bound to systems created and updated through interaction. To send a quantum state is not only to send a message, but to extend correlation across space. Still, even with perfect predictions, quantum mechanics leaves a lingering question. What does it mean? The equations work, but interpretations differ. Copenhagen treats the wave function as a catalog of outcomes. Many worlds removes collapse by branching reality. Pilot wave restores definite trajectories guided by a hidden wave. Cubism reframes the wave function as an agent's beliefs. And yet, remarkably, the experimental predictions remain the same. The math keeps working no matter which story we tell. Maybe that's its quiet beauty. Quantum mechanics doesn't offer certainty. It offers mystery shaped by precision, and perhaps understanding isn't only collecting answers, but learning how to ask better questions. Gently, in a universe that seems to hold many stories at once. And so we reach the end of tonight's quiet journey through the quantum world, where certainty dissolves, probability hums, and even empty space is full of potential. If you enjoyed drifting through these 101 quantum facts, leaving a like truly helps. Small signal, big impact for the algorithm, and it helps other curious minds find this calm corner. If you're new here, consider subscribing to Sleepy Scientist for more gentle explorations of science and space. And if you're already subscribed, thank you. tap the bell if you'd like a reminder when the next video is ready to drift into. And if there's a topic you'd like explored slowly in a future episode, leave it in the comments. Until next time, stay gentle, let your curiosity stay bright, and may your night be filled with quiet wonder. If you're still awake, you can continue to the next chapter. Otherwise, I hope you sleep deeply and dream gently. Good night.